Weisfeiler for playing a key role in organizing and disseminating this the seminar series. And in fact, UNG will provide a more detailed introduction to the talk and the bio of our speaker. Thank you again.
Great, thanks. Yeah, it's my great pleasure to introduce Professor Michael Bronstein. He is a DeepMind professor at the University of Oxford. He was previously head of graph learning research at Twitter, professor at Imperial College London, and held visiting appointments at Stanford, MIT, and Harvard. He received his PhD from Techne in 2007. He's received several awards, including EPSCR, SRC, Turing World Leading Research Fellowship, Royal Society Wolfson Research Merit Award, and many others. He's also a member of the Academia European Fellow of IEEE, IAPR, BCS, and ALICE. ASAM Distinguished Speaker and World Economic Forum Young Scientist. In addition to his academic career, Michael is a serial entrepreneur and the founder of multiple startup companies, including some ones acquired by Intel and Twitter. Welcome, Michael. The floor is yours.
Thank you very much. Thank you for the kind invitation. And well, unfortunately, I need to do it remotely. For family reasons, I couldn't come in person. So I would like to talk a bit about geometric deep learning, and in particular, some of the recent works where we try to draw some inspiration from physics design of neural network architectures, in particular for learning on graphs, but more broadly. So I just wanted to say that my position at Oxford now, I think it's probably the best title in the world, because it gives me this unique opportunity to harass Google at all machine learning conferences, asking them to show me my chair. It has not been possible. I was to change at some point. So I would like to start maybe a little bit kind of philosophical introduction. So taking you back to maybe history. And if you think of one concept that was important in mathematics and in science in general, this is the concept of symmetry that, as we'll see, underlies all these constructions of geometric deep learning. And Hermann Weyl was a very important mathematician that played a pivotal role in the foundation modern theoretical physics, spoke very poetically about symmetry, as wide or as narrow as may define its meaning, which according to him is one idea which man through the ages has tried to comprehend and create order, beauty, and perfection. And in fact, the term itself comes from Greek. So the Greeks believed that symmetry was foundational to the nature itself. So for example, Plato considered symmetric polyhedra, what nowadays we call Platonic solids, named after him, to be the fundamental building blocks of the universe. He thought that all matter around us is composed of this tiny symmetric polyhedra, which, if you think of it, it's not a crazy idea, because nowadays we understand that this is how crystals are organized. And the Greeks in general considered geometry, right? So symmetry comes, of course, as a geometric concept. They considered to be geometry the most important of sciences. So Plato himself, according to a legend, had an inscription on his academy, let nobody not skilled in geometry enter here. And geometry that we still teach at school as the geometry was described by Euclid more than 2,000 years ago. And as you obviously know, it was based on 5 axioms or postulates from which all the theorems were derived, where the fifth postulate about parallel lines somehow stood out, and many illustrious mathematicians tried to prove it to no avail for hundreds, if not thousands of years, until the beginning of the 19th century, where came the realization that actually you can create other geometries that do not stick to Euclidean postulate of parallels. And this created a zoo of different geometries that didn't speak to each other, and it was not clear even what defines a geometry and how they're related to each other. So this was somewhat an unhealthy situation that required a new approach, completely different, radically conceptually different approach that came from a young German mathematician called Felix Klein. He was appointed in 1872 as the professor at the University of Erlangen in Bavaria. And as it was customary in Germany at the time, he was asked to deliver a talk about his future research at the university. And it entered the history of mathematics as the Erlangen program, where he suggested treating geometry as a space with some group of transformations. So essentially studying the way in which a geometric shape is transformed by the action of some group. And he showed, for example, that Euclidean geometry arises from rigid motions, right? So from translations, rotations, and reflections, right? What is called the E3 group. And of course, you can consider bigger groups such as affine or projective group, and gives rise to different types of geometries. And it was obviously a very big impact on mathematics in general, and geometry in particular. So you can trace the ideas of Klein, for example, in category theory that appeared in the 40s, and that's the language of abstract mathematics nowadays. But I think it's fair to say that the biggest impact was in physics, where also in the beginning of the 20th century came the realization that you can actually derive the very laws of nature from first principles of symmetry, right? And probably the most famous result is the result of Amy Noether, who showed mathematically that you can derive conservation laws that before that were considered to be empirical observations, experimental. It can be derived from notions of symmetry. For example, conservation of energy arises from the symmetry of time. And this notion, in certain evolved manner, by Young and Mills in particular, evolved into what nowadays we call the standard model of particle physics. And basically all physics that we know nowadays, maybe with the exception of some weird things like dark matter, can be derived from these considerations of symmetry. So physicists like distinguishing between external symmetry of space-time, right? So this is what is called the Poincaré group that gives rise to the Minkowski geometry that is encountered in relativity, and the internal symmetries of quantum fields that give rise to different interactions or forces between different particles. And I think it was beautifully and laconically formulated by Philip Anderson, a Nobel laureate in physics, that it's only slightly overstating to say that physics is the study of symmetry. His famous paper in Science called More is Different. Now, what does it have to do with deep learning? So in deep learning, we also face a similar situation in the sense that we have a lot of different architectures that historically were derived for different problems and different types of data, such as convolutional neural networks for images, or recurrent neural networks for sequences, or graph neural networks that originated in the context of chemistry. So basically molecules that can be represented as graphs, and so on and so forth. And apparently there is no common denominator, mathematical principles that unite these architectures. Therefore, people think that deep learning is a kind of empirical science, a collection of hacks, right? And also this is the way that it is often taught. So what we try to do with this framework that we call geometric deep learning is to try to find, maybe slightly arrogantly by analogy to Klein's Erlangen program, is to find some kind of common foundations or common principles that will allow us to derive existing architectures, but also to, in the future, derive new ones from a foundational principle of symmetry. And if you think of maybe the simplest setting of supervised machine learning, right? So you can maybe cynically think of it as a kind of glorified curve fitting, right? So you can think of a function approximation problem. You have some function that, let's say, separates between cats and dogs. So you can think of cats and dogs images as high-dimensional vectors in your input space, right? So you have some black box that takes as input such a vector and produces a binary label, right? Whether it's a cat or a dog. So of course, the question is what kind of class of functions you would like to fit to these data. And since the late 50s, in 1957, and we know that they're universal approximators, right? So we can take any continuous function represented by a perceptron layers. But this result is not really constructive, so it doesn't tell you exactly how to find the weights of these neural networks, a number of neurons. And what also appears that, of course, you can have infinitely many continuous functions that interpolate the given trainings. So you need to assume some regularity. So if I take a d-dimensional function, function of d-dimensional input that I assume to be very well behaved, Lipschitz continuous, then the number of samples that I will need to take in order to approximate it to accuracy epsilon will be exponential in the number. This means that we cannot use this kind of classical results from approximation theory. So what we try to do is to replace it with stronger geometric priors. And in this example of images, we would like to treat images not as vectors or as points in high-dimensional space, but to consider them as signals living on some low-dimensional domain. For example, a grid, right, in case of images, or maybe some other structures if it's some other types of data. And in this case, the domain is equipped with some symmetric group, right, that describes its structure, the way that points on the domain transform. And on the signals that live on this domain, the group acts for what is called the group representation. So, for example, if I have the translation group in the plane, then the shift operator is its representation when it acts on images. And the functions that take as input these signals, for example, image classification, need to respect the action of this group in the form of, for example, invariance, right? So no matter where the cat is located in the image, I would like still to be able to say that this is a cat, right? So we call such functions invariant, so they are unaffected by the action of the group, or equivariance, where the output is transformed in the same way as the input. Now, early examples of such geometric architectures, right, maybe without explicitly admitting it, actually were inspired by works in neuroscience, in particular the seminal work of Rubel and Wiesel that brought them the Nobel Prize in Medicine about the structure and organization of the visual cortex in mammals. They studied humans and cats and monkeys, and I think in humans it was also found to be roughly the same way. And basically this was implemented in machine learning architecture called neocognitron by Kunihiko Fukushima in 1980, where basically the idea was to use local connectivity, what is called receptive field, with shared weights. And then the modern version of this architecture was introduced by Jan LeCun, the classical convolutional neural networks, in the late 80s. And this is one of the standard architecture that is still very popular and used for image analysis and image classification. So if you look at it from this perspective of geometric deep learning blueprint, basically you just define the domain, you define the symmetry group, you define its representation, the way that it acts on the data, and then you define functions that respect this symmetry. So in case of GNNs, these functions are convolutions, right? So these are translation equivariant linear functions. This is how you define the linear layer from these foundational principles. Another example are graph neural networks. So that's what I would like to focus on today. So in case of graph neural networks, the domain is a graph, and the group that is associated with it is the permutation group, reflecting the fact that we don't have a canonical ordering of the graph nodes. So I can permute the nodes in any way. And in this case, we want functions that are equivariant with respect to these permutations. And this is, as we'll see, is implemented in the form of message passing. Now, I should also say that there are also instances of what is called geometric or equivariant graph neural networks. And these architectures are reasonably new. So I was often asked this question, what does the geometric deep learning blueprint give us? Can we go beyond existing architectures? And I think the answer definitely is positive, is yes now. So these architectures have now become pretty common, and I would say widespread especially in chemical applications. So when you have a graph, for example, that models a molecule, so this is a geometric graph. So nodes have also continuous coordinates in three-dimensional space. And here we have two types of symmetries. So we have the domain symmetry, right? So the order of the atoms in the molecule, which is permutation. But we also have continuous symmetry of the positions of the atoms, right? So this is typically the special orthogonal group, right? So reflections and rotations and translations, excluding reflections. So this is the data symmetry, and we can design message passing that will be equivariant with respect to both of these symmetries. And this is, for example, what is used in structural biology. For the most famous example is AlphaFold 2 by DeepMind, so the famous architecture that predicts the three-dimensional structure of proteins from their sequences. And also it is used nowadays for generative models in chemistry. For example, we can generate a three-dimensional molecule that is geometrically constrained by the pocket of the therapeutic target, right? So basically build a molecule that fits within a pocket in the protein surface. And we can also use these architectures to create new proteins. So proteins as well can be used as biological drugs. So these are two recent works that I did with my collaborators, and this one on the left is a collaboration with a Canadian company called Dreamfold that designs new proteins as biological medicines. And these ideas can be applied to many different types of data, right? Many domains. So obviously, classical examples are grids, graphs, homogeneous spaces more generally, as well as manifolds, meshes, and so on. And many classical architectures, whether it's GNNs, transformers, deep sets, graph neural networks, etc., can be derived as special instances of this general blueprint. And this is what we describe in our book that we've written on this topic. So in a sense, if you're familiar with this meme, you can think more or less of any neural network architecture as an instance of geometric deep learning, maybe with a few exceptions. But today I would like to focus on graphs, and I hope I don't need to convince you that graphs are probably the most widely used mathematical abstraction for systems of relations and interactions, right? So molecules are a classical example. We have atoms that are nodes of the graph, and chemical bonds represented as edges. And at higher levels, we can also think of interaction networks or interactomes, how different molecules interact with each other within a cell, or maybe even social networks, right, that describe the connections and relations between different people. So what are graph neural networks? Essentially, these are parametric graph functions, right? So I give as input a graph with some features. I do something to this graph, and I output, let's say, a number, right? So classical example would be in virtual drug screening. I give you a molecule, and I would like to predict whether it will be toxic, whether it will be, for example, soluble, or whether it binds to the desired target, right? And so on and so forth. So this is a very practical, very useful, and very important application. Now, the way that these parametric functions are implemented are usually in the form of message passing. So I have a node and I look at its neighbors, right? So no other nodes in the graph that are connected by edges. And these nodes, these neighbors send a message to my node, right? And I have a way to update the features in the node I using the neighbors that are received from the neighbors. And of course, the way that we aggregate this information must account for the fact that I don't have a way to canonically order my neighbors. So this aggregation must be through a permutation invariant operation, for example, a sum, right? Or it could be maximum, could be average, but typically it's a sum. Now, this is the most general architecture. We can also choose a special type of message passing functions where we aggregate by summation the neighbor features weighted by some coefficients that depend on the features themselves and on the structure of the graph. So this is called the attention mechanism. And even further simplification, we can talk about convolutional architectures where the aggregation is with coefficients that depend only on the structure of the graph, right? So if I want to write it as matrix equations, the convolutional architecture, the matrix of features, right, so that are organized as rows of this matrix X is multiplied by a fixed matrix A. In case of attentional architecture, it's a matrix valued function that multiplies X. And in case of generic message passing, it's some nonlinear operator that I denote here by calligraphic A. And what do we know theoretically? We know that under some technical conditions, in particular when we appropriately choose the aggregation operator and the message passing functions, they need to be injective. Message passing type neural networks are at most as expressive as the Weisfeiler-Lehman graph isomorphism test. So in other words, if we ask this question, what kind of functions can be computed by means of message passing, this gives us an upper bound, right? And what is the Weisfeiler-Lehman graph isomorphism test? It's a way of determining whether two graphs are structurally equivalent, right? Whether are isomorphic, whether I can establish a bijective correspondence between the nodes that preserve edges. So the way that it works, it's iterative color refinement. It starts with a graph where every node is colored or labeled in the same way. And it considers the structure of a neighborhood of every node, right? So, and you can see initially we have neighborhoods of two types, right? So we have nodes with two neighbors and nodes with three neighbors. So if I apply an injective function to these structures, I will get two different colors, right? So this will be the new coloring of these graphs. I can repeat this procedure again. So now I have three types of neighborhoods, right? And these will correspond to three new labels. And after some time, the labels will stop changing. So I can output a distribution, right? So that's a kind of graph level descriptor. And if these distributions are different, I can guarantee that the graphs are non-isomorphic. But if the distributions are the same, then we actually don't know. So it's a necessary but insufficient condition for graph isomorphism. So, right, so it means that these tests cannot necessarily solve all possible non-isomorphic graphs. So this is what we know in theory, right? So the WL test, right, and the analogy between message passing and WL test allows us to discuss the expressive power of graph neural networks. In practice, though, we see that some non-isomorphic graphs cannot be tested. And we also see that basically this very practical problem to send messages on the graph, some graphs might be unfriendly for message passing, right? So if I need to transfer information from this blob to this blob, it all goes through this single edge that connects them, and information must be lost, might be lost on the way from one blob to another. So the solution to the first problem is, for example, resorting to a hierarchy of high-dimensional KWL tests, right, without going into too much details. Basically, they're increasingly more expressive, and of course, there are always families of graphs that they cannot distinguish, and you can design graph neural architectures that are equivalent to these KWL tests, or upper bounded by in their expressivity by them. The solution to the second practical problem is to decouple the input graph from the computational graph, right? So you can say that if this graph is not friendly for message passing, let's use a different graph to send the information, right? So this is generally known as graph rewiring techniques. And there are many approaches that tell us how to design these graph so the flow of information is improved. So you can obviously see that there is a gap between theory and practice. So the theory tells us that I need to follow exactly the same graph in order to make this equivalence between message passing and Weisfeiler-Lehman. But in practice, we know that this might be detrimental in some situations. So basically, that's the classical GNN, and we can, of course, augment the graph with some more structure, right? So, for example, the most commonly used one is positional encoding, right? So we add some extra features. This is very commonly used in transformers, right? But also in graph neural networks more generally. We can lift the graph to some high-dimensional topological space, to a cellular complex, for example, and do message passing across cells of different dimension. We can consider the graph as a collection of subgraphs that are extracted by some policy. So this makes analogy with reconstruction conjectures, and it's strictly more powerful than WL. And then what I mentioned already, accounting also for the symmetry of data in the form of equivariant message passing, or when the graph has a special structure like a grid, then we can make the message passing functions more specific and actually position. We can order canonically the neighbor nodes. So on the other side, we can ask the question: how much do we want to rely on the input graph? So in the one extreme case, we can say that we totally disregard it, right? So we consider now just the set of nodes of the graph. And these are architectures that are known as deep sets or point nets. And the other extreme, we can allow any pair of nodes in the graph to interact. So this is how transformers work, right? So transformers are GNNs with latent graph, right? That is learned through the attention mechanism. So graph rewiring techniques sit somewhere in between. So we do want to rely on the input graph, but we might want to change it because the input graph might not be necessarily the best one to propagate information. Now, another thing that you notice if you compare different domains that arise in geometric deep learning, right? So graphs, grids, and meshes, for example, we can see that the way that we aggregate information is very different on these domains. So on the grid, we can canonically order all the neighbors, right? So there is no ambiguity whatsoever as to the ordering of the nodes. On a mesh, I can designate the first neighbor and then order all the rest of the neighbors in a canonical way, right? So it's a discrete manifold, so we can there is a sense to a notion of, for example, clockwise orientation, right? But the choice of the first node is ambiguous, so it's defined up to rotation. On the graph, as we've seen, any permutation works, right? So in a sense, graphs have the least structure, right? So the aggregation here is the weakest in a sense. Another thing that you notice is that we can think of grids and meshes as discretization of continuous objects, right? So a grid is discretization of the plane, a mesh is discretization of a surface. We don't have immediately such an ambiguous analogy for graphs, right? Even though, of course, you can think of continuous models for graphs such as graphons or entire field of network geometry, right? That tries to think of graphs as sampling of some continuous space, for example, hyperbolic space. but what we want to do is to try to derive some continuous models for graph neural networks, right? And this is what we call physics-inspired GNNs. And for the purpose of this discussion, the mental picture I would like you to have is to think of a dynamic system where every node of the graph is a particle in some d-dimensional feature space that moves along some trajectory, right? So basically, we would like to think of graph neural networks from this perspective of a continuous dynamic system, right? So every node in the graph is a point in some d-dimensional feature space, right? So it evolves according to some trajectory. So the trajectory is a function of time, right? So that's these are the coordinates of all the nodes of the graph assembled in a matrix, right? So it's again a matrix that depends on continuous time variable t. N is the number of nodes, d is the dimensionality of the coordinates. They are governed by some system of differential equations written here, right? And these are the trajectories. So if I discretize this time with some fixed step, or it doesn't need to be fixed, but for simplicity, let's consider fixed time step tau. I can think of these as layers of a graph neural network, right? So the differential equation now becomes the difference equation that is written here. Now, what is the role of the graph? You can think of it as a coupling function, right? So the particles don't live on their own, they interact with each other, and how they interact along the edges of the graph, right? So the graph appears here as a coupling function. So this function f tells us how the rows of these matrices interact with each other in the evolution equation. We'll see also that in some settings we can think of the graph as a discretization of some continuous object, of some continuous space. So now, out of all these possible differential equations that govern the behavior of this system, so probably the first one that comes to your mind when you think of how things propagate on a domain is the diffusion equation, right? And this was also described mathematically as probably one of the early physical systems to have a formal description by none less than Isaac Newton himself in an anonymous paper in the Transactions of Royal Society published in 1701. And he described an experiment with a homemade thermometer and also a law that nowadays is known as the Newton law of cooling, which tells us that the temperature a hot body loses in a given time is proportional to the temperature difference between the object and the environment, right? So that's a description of how heat propagates in an object. So it's a kind of a global rule, but we can apply it more or less to anything. So we can apply it to temperature, we can apply it to chemical diffusion, we can even apply it to propagation of rumors on a social network. So this is how it will look on the graph, right? So think of nodes of the graph as having some quantity, let's say temperature. So here I color coded red are hot nodes and blue are cold nodes, right? So xi in this case will be the self temperature of the node, right? Here, the sum is the average temperature of the neighbors, right? So that's the temperature of the environment. And then the rate of temperature change is the temporal derivative, right? So that's a local differential version of Newton's law of cooling written on a graph. Now, allow me to rewrite these equations slightly different. So the right-hand side can be written like this. And what is written here in the brackets is a discrete version of the classical gradient operator from calculus, right? So what it does, it takes features that live on the nodes of the graph, takes the difference between them, right? And it gives us a signal that lives on the edges of the graph, as we call the gradient of this field. The summation that is written here is the discrete analogy of the divergence operator. So it's the opposite operator, technically speaking, the formal adjoint. So it collects data that lives on the edges that share a node and sums them up to give, again, a signal that lives on the nodes of the graph. So together, the divergence of the gradient or minus divergence of the gradient is called the Laplacian operator. And the Laplacian operator, what it does, it compares a node to its neighborhood, right? So it looks at the difference between the node and the average of the neighborhood. And this operator appears more or less in every equation of mathematical physics. It's ubiquitous because we often need to compare ourselves to our environment. And this is the simplest version of the homogeneous isotropic heat equation on the graph. Now, what we also know about the heat equation is it's a prototypical example of a gradient flow. So what is a gradient flow? It's a variational version of steepest descent. So it's an evolution equation where the update, right? So the time increment in the features follows the negative direction of the gradient of some energy that is denoted here by this calligraphic E. And we know what is the energy that corresponds to the heat equation. It's called the Dirichlet energy, right? So you can write it as this quadratic form with respect to the Laplacian. And what it measures is the smoothness of the node features. So it is decreased along the flow, right? So if I run the heat equation to infinity, everything will become constant, right? So all the temperature will become the same at all the nodes of the graph, right? And it means that the Dirichlet energy in this case will be zero, right? So the norm of the gradients, right? So all the gradients will be zero, the norm will be zero. And in graph analytics, usually this is referred to as oversmoothing, and it's considered a kind of undesirable phenomenon, but it's not necessarily bad, right? It depends on what you want. So you can, if you know that your graphs are homophilic in the sense that for example, the labels of the neighbors are similar to the node itself, I can just solve a very simple heat equation with boundary conditions. So if I know the labels of some nodes, I fix them as boundary conditions, and I diffuse these labels to the rest of the nodes of the graph that are unlabeled. And this way I can infer these labels. It works extremely well when the graph is homophilic. If the graph is not homophilic, then of course it doesn't work, right? So we need to do something else that would involve some form of learning. Now, back to the mental picture of this dynamic system. So the typical approach to designing graph neural networks from this perspective is you start with an evolution equation, you discretize it, right? So it becomes a difference equation, and then each difference, right, or each iteration of a numerical solver that you use to solve this differential equation, it's parameterized by its own set of parameters, right? So this corresponds to a layer of a graph neural network. I would like you to suggest a different analogy, which we call the gradient flow framework. And in this case, we start with an energy that is parametric. We parameterize an energy, and we derive the evolution equation as a gradient flow. And what we gain in exchange, of course, not every evolution equation is a gradient flow, so it already restricts our architectural choices. But what we gain in exchange is some better form of interpretability. And I know that interpretability is somewhat controversial term in machine learning. So what I mean by interpretability is that we'll be able to show mathematically that certain types of, basically what we would like to be able to show is certain mathematical guarantees of behavior. And in particular, we would like to show that we can avoid oversmoothing. And this is again the situation when all our features collapse into a single point, right? So if I give you an example of these graphs, so every node here is color coded according to its label. So we have blue nodes and red nodes, and you can see that this graph is perfectly heterophilic, right? So you can see that blue nodes have only red neighbors and vice versa. The positions of the nodes represent the coordinates in the feature space, right? So d-dimensional coordinates. And the task here is node classification. So I would like to be able to pull apart the reds and the blues, right? So we would like to be able to separate them completely. And you can see that it's possible, right? So here are trajectories that allow to do basically this perfect node classification. So what we do in this case, so we use a parametric energy that looks like a Dirichlet energy. It's parameterized by this matrix W. So the matrix W acts on every node in the same way, right? So it acts on the coordinates of the nodes. And basically this energy induces two types of interactions. So attractive interactions happen along the positive eigenvectors of W, right? So this here is represented by the vertical dimension in this plot, right? So the nodes come close together. And we also have repulsive interactions that happen along the negative eigenvectors of W, which pull the feature coordinates apart. And the evolution equation that is the gradient flow of this energy, it looks like this. So you can see that this is what we call the convolutional architecture, right? Because the matrix A that diffuses the node features on the graph is constant. It's independent of the node features. And what we can show is that this kind of linear graph diffusion, right, or convolutional GNN, if we appropriately design the channel mixing matrix, in particular, we need it to be symmetric, so we can guarantee that this is a gradient flow, and we want it to have sufficiently large negative eigenvalues that is to induce these repulsive interactions, can provably avoid oversmoothing. And this is a result that goes against the folklore in graph neural networks. You often hear that these kind of simple convolutional type architectures are too simple to be able to deal with heterophilic graphs. And usually the motivation that is given is that this matrix A acts as a low-pass filter. So if my neighbors are different from me, I will be averaging unrelated things, right? So like apples and oranges. But the reality is more interesting and more nuanced because we have now two matrices, right? So we have interaction between this diffusion matrix A and the channel mixing matrix W. And it's the interaction of their eigenvalues that is important for to determine this behavior, whether everything will collapse into a single point or not, right? And that's why this matrix is required to have sufficiently large negative eigenvalues. So we can also show that it really works both in homophilic and heterophilic cases. So here is a synthetic graph where I can continuously change the level of homophily. And the two extreme cases that we test here is completely ignoring the structure of the graph, right? So here again, the task is node classification. So we can just apply a node level MLP to the node features. And you see that it doesn't work very well, but at least it's totally unaffected by the level of homophily in the graph. The other extreme case is to use a GCN. So GCN would be exactly this kind of naive averaging filter. So it works very well when the graph is homophilic, but it deteriorates in its performance when the graph is heterophilic. You can see that the gradient flow framework takes, in a sense, the best of both worlds. So it performs as well as GCN when the graph is homophilic, but then it doesn't degrade as badly as GCN when the graph is heterophilic. Now, this was the simplest homogeneous diffusion equation, right? And if we see how it works on images, right? So when we assume that our graph is agreed, then we actually have a closed form expression for this type of diffusion. We can write it as convolution with the Gaussian kernel, where the variance of the Gaussian increases with time, right? So if you look at the kernel of this equation, it is homogeneous and isotropic, right? So it's the same at every point. Of course, if you look at the result of this diffusion, then it might remove noise, right, by averaging it out from the image, but it also destroys important discontinuities between the pixels and the images. So what was developed in the 90s, starting from the seminal work of Perron and Malek in 1990, is to locally change the speed of diffusion. So they mistakenly called it an isotropic diffusion, but in fact it's isotropic but not homogeneous. In an isotropic diffusion, we also, the diffusion speed depends on the direction. So here it depends only on position. And the way that it depends is through the strength of the discontinuity, right? So we have an edge indicator that is described by the norm of the gradient. And basically what we want to do is to avoid diffusion across edges. So if I have my kernel at this point and it works on dark pixels, I don't want to mix dark pixels with bright pixels. So if you think of it, it is extremely similar to the mechanism of attention that is used in deep learning. It's just a fixed and not learnable kernel. And we would like to do something like this on graphs, right? So you can see that you can write a non-homogeneous diffusion on a graph in this way, right? So we have this diffusivity function. It is learnable. It's a parametric function. So that's exactly the attention function. If I discretize this non-homogeneous diffusion equation with some assumptions about the step size and normalization of the diffusivity, I get the classical graph attention network, right? The GATT architecture. So you can see that we can derive convolutional architectures as isotropic and homogeneous diffusion is discretized, and the attentional architecture as non-homogeneous diffusion equation of graphs. Now, I remind you that I wanted a continuous model for graph neural networks, and so far the only thing that we were able to do is continuous notion of layers, right? So we have continuous time. Now we want to do continuous space, right? And if again we look at how diffusion equations are discretized in the plane, so I discretize the plane as agreed, and now the way that we discretize the differential operators, the spatial differential operator, the Laplacian, we can really have many ways of doing it, right? So here I show 3 different discretizations of the Laplacian, and any convex combination of these discretizations is also a valid discretization, right? It's a linear operator. So the point I'm trying to make here is that we don't really have a canonical computational graph when it comes to the diffusion equation in the plane, and we would like to adopt the same mindset for graphs. And in order to do it, we would like, instead of considering nonlinear diffusion equations, as we've seen before, we would like to consider non-Euclidean diffusion equations. And what I mean by non-Euclidean is, again, if we take this analogy of images, I can think of an image as a manifold that is embedded in a joint space where we have every pixel has positional coordinates, right? It's x, y coordinates in the image, and feature coordinates, which are the color channels, right? R, G, and B channels. And by virtue of this embedding, we can pull back a metric, right? So two-dimensional 2x2 matrix, right? Riemannian metric on this manifold, with respect to which we can define a non-Euclidean version of the Laplacian operator, what is called in differential geometry the Laplace-Beltrami operator. And again, with respect to this operator, we can write a diffusion equation that is called the Beltrami flow, and it appears to be a gradient flow of a generalization of the Dirichlet energy that is called the Polakov function, right? So it's harmonic energy of embedding used in string theory. So it describes bosonic strings in high energy physics. So same idea could be applied to graphs, right? So now every node comes with the feature coordinates and positional coordinates. So positional coordinates roughly represent the structure of the graph. And now we evolve both of these components. I denote them together by Z, and they're coupled through this diffusivity function that again is learnable, this function A. And the evolution of the X coordinate is standard feature diffusion. The evolution of the U coordinate is a kind of soft version of graph rewiring, because if two features come close together in the U part of the space, I can introduce an edge between them to facilitate the flow of information. Same way, if they drift apart, I can decide to disconnect them. So maybe this animation shows it much better than I can describe. So this is again a Cora graph. So here we are trying to classify nodes. There are 7 classes. And you can see that 3 things are happening at the same time. So the color of the node represents here a low dimensional projection of the features. The positions of the circles represent some positional coordinates. So we are diffusing both, right? So the colors are changing, the positions are changing, and the graph is changing. The graph is being rewired. And if you think of it as from the perspective of classical harmonic analysis, basically what you see here is a kind of, we have a filter that runs on the domain that is changing at the same time as we are filtering, right? So it's a kind of shaky ground, right? So the ground is moving under our feet, which is a somewhat disturbing picture. But if you think of it from the perspective of differential geometry, this is actually a very common thing to do. Differential geometers like to take a manifold and subject it to some evolution equation. And when we say manifold, we are talking about evolution of the Riemannian metric, right? So probably the most famous of these evolution equations are Ricci flows. So structurally, they look very much like the diffusion equation. So here we have the temporal derivative of the metric, right? And on the right-hand side, we have the Ricci curvature tensor, which is second order quantity similar to the Laplacian, right? So structurally, it looks like the diffusion equation. What it does to this manifold, so in this case, it has positive curvature on the spheres and negative curvature on the bottleneck. Basically, we have an evolution that starts with this dumbbell-shaped manifold. And if we run the Ricci flow backwards in time, then this dumbbell-shaped manifold becomes more like an ellipsoid than like a sphere, and then collapses into a point. And the reason why Ricci flows were introduced by Hamilton in the 80s was to prove the Poincare conjecture. So as you probably know, what Poincare conjecture does, it describes topological spheres by the ability to take a closed curve and collapse it into a point. So you can do it on a sphere, you cannot do it on a torus, right? So if you have a curve that goes like this, I cannot collapse it into a point. So the conjecture was that it also holds in higher dimensions. And as you know, Grigori Perelman proved that this Holy Grail problem that stood open for more than 100 years using Ricci flows, and topologists were appalled that their Holy Grail problem was solved by differential geometry. Now, what does it have to do with graph neural networks? So remember that we mentioned this problem of the difficulty or the failure of message passing to propagate information on the graph. And it appears when the graph has such a structure where the number of nodes increases exponentially with the radius, right? So if I look at a tree, for example, then the number of the neighbors of the neighbors of the neighbors will grow exponentially fast. So if I add to it also the task that requires long-range interactions, right? So if in order to compute my function on the graph, I need to communicate between distant nodes, then I get into a situation where I need to bring a lot of information from distant nodes, squeeze them into a single vector. This is called oversquashing. You can see there are 2 components to it. So the structure of the graph and the structure of the task. So let me start with the structure of the graph. And basically the way that we can describe the problem of oversquashing is considering a message passing architecture with multiple layers, right? And let's denote the characteristic of this architecture, like the number of layers, the number of neurons, the activation function, the bound on the weights by these numbers, right? L, P, C, and W. And what we would like to ask is the following thing. So let's say that at node I, this message passing architecture produces some output, right? Let's call it Xi. I would like to perturb the input at a distant node J and see how this perturbation propagates by message passing on the graph, right? So this is given by a partial derivative, right, or the Jacobian. So I can look at its norm, and if this norm is small, it means that somehow this perturbation is lost on the way from node I to node J, right? So basically, a small value of this Jacobian in its norm indicates poor information propagation, right, or insensitivity, right? And this is what we call oversquashing. So the main result of this paper is a bound that we can bound the norm of the Jacobian by parameters that relate to the model, right? So these are the number of layers, depth, and so on, as well as the topology of the graph, right? So here it comes in some modified adjacency matrix, right? So we know that both are important for oversquashing, and usually what we can change easily is the model, right? So I can add another layer to my graph neural network, or I can change the number of neurons. So the topology of the graph, at least in classical graph neural networks, is fixed, right? So the graph is given and I use it to propagate information. So in graph rewiring, this is what I'm trying to change, right? And you see that the structure of the graph appears here, but it's not clear in which way, right? So intuitively, we know that something that looks like a grid is better for message passing than something that looks like a tree, right? So in a tree, the number of nodes grows exponentially, right? So the number of neighbors, so the volume growth is much faster. So we need some kind of mechanism that allows us to distinguish between these situations, and that's exactly where Ricci curvature comes into our to our help. So I remind you that in continuous setting on manifolds, we can think of curvature as geodesic dispersion. So I can take nearby points, I can shoot geodesics from them. If geodesics converge, I locally look like a sphere. If they remain parallel, right, like in the classical Euclidean geometry that we started with, then the curvature is zero, and this is a flat space. And if they diverge, right, like in hyperbolic geometries, that again were the first examples of non-Euclidean geometries constructed in the 19th century, we are talking about negative curvature, right? So an analogy of this quantity on the graph would be a discrete Ricci curvature. So there are several ways of defining it. Here we are talking about a curvature that is defined on the edges of the graph. I take 2 nodes connected by an edge, and I look at edges that emanate from these nodes. And I can count some combinatorial structures such as triangles and rectangles. So if these edges tend to form triangles, I'm looking at clique-like structures, right? So we can say that we can define the curvature in a way that will be positive for these structures. If I count certain number of rectangles, then I locally look like a grid, right? In this case, the curvature is zero. And if the nodes, if the edges drift apart, then I have negative curvature and it looks like a tree. So the main result of this paper is that we can attribute oversquashing to the presence of strong negatively curved edges in the graph. And once we can do it, we can rewire the graph by surgically removing these negatively curved edges and replacing them with edges with higher curvature. So it acts a little bit by analogy to the Ricci flow, right? So basically, it somehow homogenizes the curvature, and we show that it improves the message passing and the performance of graph neural networks, both in homophilic and heterophilic settings. Now, the main problem with this approach is that it totally disregards the task that we are trying to solve. And here's an example why this is important, right? So I can give you a graph. Let's give an example from chemistry. So the graph, in this case, represents a molecule, right? So nodes are atoms, edges are chemical bonds, and the molecules, as you probably know, we have different types of forces, right? So the atoms can interact in different ways. So one of the forces is electrostatic force. It decays as 1 over the radius, right? So it's very long and very slowly decaying force. Another type of forces are van der Waals interactions, right? So they decay as 1 over r to the power 12. And you can ask the question whether the given graph, right, that is a local connectivity following the chemical bonds, in the molecule is good to compute these forces. So, and you can imagine intuitively that probably for van der Waals, because it's very local, then this graph is probably good. For electrostatic, probably not good, and you want to also bring information from distant nodes. So this is an example where we have the same graph, two different tasks, and whether the graph is good or not for message passing depends on the task, right? And this brings us to the basically to the relation between long-range interactions and expressive power. So we want to account for the task, and the way to account for the task, basically, we want to first of all describe the task in some way, right? And when I say task, I mean a function that depends on the graph and the node features. And the way that I would like to characterize this function is through what we call mixing. So mixing, here we define it through mixed second-order derivatives, elements of the Hessian matrix. And roughly what it gives us is if our function is fully separable, right? So when I have, I can write it as some nonlinearities that depend on the individual node features, it is fully separable. Basically, here the second-order derivatives will be 0, so mixing is 0, right? I don't need to propagate information between nodes at all, right, to compute this function. The other extreme is a function that is written as some nonlinearity of the inner products between the nodes, and in this case, the mixing depends on how nonlinear the function phi is, right? So basically, what we want is some kind of capacity bounds. So I can ask the question: if I give you a message passing graph neural network, what kind of functions can be computed by this architecture, right? Or maybe the other way around, if I give you a task with certain mixing, what kind of model would be required to compute this task, right? So basically, we want to link together the task that is characterized through mixing and the MPNN that is characterized by the model parameters, like the number of layers, the number of neurons, and so on, as well as the topology of the graph that is used for message passing. And you see that in this bound, all these three quantities come together, and we can describe the bounds on the weights, but probably more interesting bounds on the depths. So I can say that I need a certain minimum number of layers that depends on both the topology of the graph, the mixing of the task, and the parameters of the architecture. And we see that, for example, the depth must be proportionate to the commute time. So it means that in theory, it can be very large. So it leads to impossibility statements. And we can also see, and this is another result from our recent paper, that rewiring approach is trying to improve the commute time on the graph. So they try to reduce it. So some graphs have optimal commute time, such as expanders. So this is also an approach that was introduced relatively recently to use expanders to propagate information on the graph in message passing. And basically, this allows us to go beyond the Weisfeiler-Lehman. Basically, we can go beyond the Weisfeiler-Lehman formalism to basically to state the expressive power of graph neural networks. We can say that an MPNN with a certain number of layers cannot learn tasks that require high mixing among nodes with too large commute time, right? So that would be basically the kind of results that do not resort to the formalism of Weisfeiler-Lehman graph isomorphism tests. So last thing that I would like to mention is basically we talked about basically we're talking about different flavors of graph neural architectures. We ask the question, what kind of information to send, right? So how to transform our neighbor features and how to aggregate them. When we talked about graph rewiring, we'll ask the question where to send this information, right? So whether we are getting messages from our immediate nodes, or maybe we subsample them, right? Or maybe we can also connect distant nodes. But again, I remind you that we want to think of graph neural networks as dynamic systems, right? So the important ingredient that is missing is when to send this information. So let's look at this example. So we have this little graph, and I want to propagate information from the red node to the green node, right? And you see that in classical message passing, it will take 3 steps of diffusion, right, or message passing. So first, the information goes to the neighbor, then from the neighbor to the neighbors to its neighbors, and then it arrives at the green node, right? And on its way from the red node to the green node, these messages will also be entangled with messages that come from other nodes, right? So this information, as we've seen, in the analysis of oversquashing might somehow be lost on the way. So in graph transformers, where the graph is fully connected, the information from the red node to the green node comes at once, right? But what we also get is information from all the nodes in the graph, right? So in this case, we might be overwhelmed by messages that are completely irrelevant for the green node, right? So we want some kind of middle ground. So we call this dynamic rewiring, and basically we gradually increase the receptive field. So basically we expose the information from the red node to the green node gradually as it would appear in classical message passing. And we can also introduce a delay mechanism. So we call this architecture Andrew, so dynamic rewiring with delay. And it takes the form of sparse skip connection. So we know that the information from the red node will arrive after 3 steps to the green node, but it will be also mixed with other node features. So we can send it directly with delay that would be appropriate to the time that it takes to for this information to arrive to the green node. And we show that this architecture is more general than transformers. It also works better on long distance tasks, on benchmarks that were established for these kind of problems. So last thing I would like to show is that, well, you can think basically more or less 99% of graph neural networks are based on message passing. What else can we invent instead of message passing? So, but let's look at it from this perspective. So basically, in a classical message passing, every node it has 2 functions. So it receives information from the neighbors, but it also sends information to the neighbors, right? So the edges in the computational graph are bidirectional. So basically, they come in and they go out. Now, what we can try to do is for every node separately, we can decide whether it sends or listens or does both or does nothing, right? So basically, we have 4 different states. The node can broadcast and listen, right? Like in standard message passing, it can only listen, it can only broadcast, or it can isolate. In this case, it does nothing. Basically, this might happen that at some points in my graph neural network, the node should be sending information, but maybe at some point it will become irrelevant. So I would like to tell this node to shut up, right? And this allows us to basically have a directed computational graph that is also dynamic. So we have a separate mechanism that decides for every node based on the downstream task, what should it be doing at every layer. And we can route the information in a more flexible way. We can also show, so this is a stochastic architecture. Basically, the choice, the sampling of the actions is not deterministic. So therefore, all the results like permutation equivariance are in expectation. But we can show that it's strictly more powerful than WL, and it probably allows to avoid oversmoothing and oversquashing. So to conclude, basically, what do we gain from this physics-inspired approach? I think it gives a new perspective on old problems. So we can look at problems like oversmoothing and oversquashing. We can explain existing architectures and derive new ones. Maybe more importantly, because message passing is a vast class of architectures, we can make principled architectural choices. For example, decide if we want to have residual connection or shared weights, or maybe have symmetric weights like in our gradient flow framework. We can provide theoretical guarantees like the example that we've seen, right? Like about stability, convergence, lack of oversmoothing. I didn't show maybe some more exotic forms of diffusion, so we can do diffusion on cellular sheaves. But basically this gives links to more interesting parts of pure mathematics like algebraic topology, but links to differential geometry that I showed today, I think are also interesting. They're probably less known in machine learning literature. And also we've seen that we can, in a principled way, separate between the input graph and the computational graph, right? So we can tell which graphs are better for propagation of messages and rewire them in a way that probably improves this propagation, and also not only consider what kind of information to send and where to send it, but also when to send it, right? So the dynamic aspect of graph rewiring and information propagation. So I think I'm done here. So thank you very much for your attention.
So yeah, we can take a couple of questions. Like I can start with the first one. So Michael, you mentioned a lot of like physics perspective message passing, and you also mentioned this disentanglement of input graph and the computational graph. Like this might be a kind of like philosophical question. If something is really good for computation, does it mean the nature will favor this way? Have you done any of like a showcasing or interpretability to show, yeah, maybe nature actually does? For example, in molecule, we do this local, yeah, you have show wonderful pictures about van der Waals force and Coulomb force. So do you have any comments on that?
Yeah, so it's an interesting question. So I think at least my take on this is that it's kind of mixed results. So we try to see, for example, whether the latent graphs that you learn with some mechanisms can be interpreted. So in some cases, it can interpret them. In some others, it's just a graph that is for the task, but doesn't necessarily have any interpretability. So we had also some follow-up works where we try to learn latent simplicial complexes. So basically higher order relations between nodes. And we see that in some cases, if we ignore the graph and we learn latent simplicial complex, it actually works better than if we use the input graph. So it means that the graph fails to capture all the higher order relations between the nodes. So it happens in some data sets. Yeah, something that unfortunately I can say that somehow the optimal graph for solving the task is necessarily the one that you can interpret.
Thank you. More questions?
Maybe a follow-up, and I was wondering if you could, put this work in perspective. And I back when Paul had the message passing algorithms, essentially the idea was, well, this works well on trees, but don't try anything with cycles, correct? And later on, actually, even for coding, it was shown that actually it even works well with cycles. So do you have any further insights about these trade-offs? And in fact, from your presentation, you actually seem to have a different perspective in terms of what's more useful, or what works best.
Yeah, so cycles in principle are not necessarily detrimental, right? So, well, if you think of diffusion equations, so I should say that here we consider primarily undirected graphs. There are some nuances when working with directed graphs, so it's in general not a problem, but the diffusion equations look differently, and then gradient flows might be more problematic to write in case when the diffusion matrix is not symmetric. I should say that cycles are actually a good feature in certain cases, in particular in chemistry. So you encounter them very frequently in organic molecules. So we usually use them as some form of structural or positional encoding, right? So you can count certain substructures in it. And if you do it in appropriate way, right? So we use the recent paper, we use homomorphism basis. So it gives you a much more granular expressive power rather than WL. So WL counts certain structures and cannot count certain structures, right? And KWL can count other structures. But you might not need all these structures for the task that you're trying to compute, right? So basically, with this idea, you have control over the right expressive power for your task. Again, I didn't have time to talk about it, but basically there are cool things that you can do with counting structures.
Yeah, so I indeed from your talk that was clear, which is quite different from the basic insights back, the original works on the message passing, etc. But I wonder if and could it be also the scale of the problems, like when we look at molecules, they are relatively small, correct?
Yeah, so
when you
can apply
very large graphs. So, and you talked about long-term dependencies, etc. Do you think this may change dramatically with scale?
I don't think so. So we tried on graphs that are very large, so with hundreds of thousands of nodes, or sometimes even millions of nodes. Yeah, not only molecules.
Very good. Thank you. There's another question.
Do I need to speak there or
You just like.
No.
Oh, yeah, okay. So my question is kind of like, I think you talked about the graph rewiring to solve the oversquashing problem and the long range interaction somehow. And I think essentially if you do graph rewiring, it's kind of like we do some modification on top of the graph structure. And there are some current works like recent works, they want to just like do some graph tokenization based on the subgraphs, and they want to treat like this kind of like a tokenization as a sequence, and they can use some sequential model like Namba, like those state space models to solve this long-range interaction problem, like oversquashing problem. How do you think, like from the perspective of the topology, like we do graph rewiring, or we just use this expressive sequential model to solve such a problem? What do you think of? Like, do you have any comments?
Yeah, good question. Well, we also had our own paper like this, where we basically you process a graph, basically you convert it into a sequence of tokens, and then you feed it into a pre-trained LLM. And well, we use ChatGPT, so actually ask questions about the graph, right? So it actually works very well. So it's probably one of the first steps towards foundational models for graphs. So of course, one of the issues is that how you can encode different graphs in the same way, right? That apply a common model rather than train a model specifically on that particular set of graphs. So I don't think that LLMs are the right architecture, because basically you break the structure of the graph. I would say it should be some form of message passing. So probably the better direction is the model that my collaborator Maxim Galkin Intel proposed, that is called Ultra. So that's probably basically it's also probably one of the first foundational models for graphs.
There's a question on Zoom. Do you see from Barton? Do you see text diffusion score-based generative models, for instance, or indeed a generative flow or probability flow coming to complement or supplant language models for language tasks? How to think about semantic and is optimal transport of information relevant in this setting? I'm not sure it's related to the talk, but
well, I don't think that I fully get the question, and I don't know what this link is. I'm not familiar with this paper, so it's a little bit hard for me to.
All right. Yeah. Yeah. We can have one last question.
Hey, Michael, I have kind of a related question, not the Zoom one, the one before. So suppose you have a transformer type of architecture that gives you a graph on the fly, but you have a very strong prior on what the graph should be like. For example, you might from the prior, you might think your data is lying on some constant negative curvature, like a hyperbolic space. I was wondering if it could make sense to use this curvature rewiring idea to impose some sort of regularization on the transformer model, if that makes any sense.
Yeah, so I know that it has been done for classical applications of transformers and NLP. So there was a group from Jacob Andreas at MIT that tried to do it like this. So they basically had some kind of tree-like structure. So it was also imposed by some assumptions of hyperbolic geometry. So the attention becomes sparser, so it has certain structure. And yeah, I think it's a good idea.
Let's thank Michael again for joining us today.
Thank you.